I'm going to talk about the deep learning. Okay, since deep learning is a very good area, in the same sense, when I talk about deep learning, I don't need to justify applications. There are many successful examples for deep neural network and deep learning. But comparing with its successful applications, many success examples of applications, the mathematical understanding of the deep neural network and deep learning seems lag behind. And to understand the deep neural network and deep learning, I think all kind of mathematics involved. And we need all kind of mathematics to really get to understand what really deep learning is doing. Today, I'm going to look at the angle of deep learning and deep neural network from the approximation point of view. And approximation theory is a classical area. Okay, at the start, maybe together with when analysis start. Whenever you talk about analyze a function or computing a function with or without a computer, you are talking about approximation. So what's new from this deep learning provide to us? Okay, this deep approximation is different from the classical approximation, and this is what I'm going to talk about. It. So therefore, to understanding a deep learning, we are not say just look at the available theory. Hopefully, all the theory kind of move in and to explain everything. In fact, I believe we needed to develop a new theory for this area. So I will start with a simple and brief introduction about approximation theory, even for the classical approximation theory. Then lead us to what kind of approximation theory we need for deep learning. And the key difference from the approximation theory we are developing now to the classical approximation theory is approximation through the compositions. Surprisingly, and we don't have many theorems about a composition of function. Okay, you think about it, you learn calculus, how many theorems you remember, it's which really deal with the compositions of a function, 10 theorems, right? Beyond that, you don't have many. So, but deep learning, approximation for the deep learning, really the approximation through the compositions. Then another fundamental question, this third part is very technical in the sense, neural network is basically about the number of neuron. What number of neuron equal to the width of the neural network and the depth of the neural network. So the width times the depth is number of neuron. So how do you calculate your approximation rate in terms of width and the depth, or in terms of the total number of neuron? And everybody whoever doing deep learning, they know this universal approximation property. So the universal approximation property is that, okay, theoretically, all kind of property, people always say, you can approximate a function, a classical function, say a continuous function, whatever, as close as you want to, as long as your number of neuron go to infinity. Okay, that's the general theory for any deep learning or shallow learning or approximation, even like a Weierstrass theory. You want the polynomial to approximate the continuous function as close as you want to, your degree has to go to infinity. But here I want to say we design mathematically computable neural network, which can be dense in the continuous function space with a finite number of neurons. So that was very surprising. That's our recent result. Okay, let me start with the approximation theory. Brief introduced to the approximation theory. Okay, So approximation theory, fundamental question you want to ask that you're given a function f, okay, given the error epsilon. You want to find a simple function which is either easy to understand or easy to analysis or easy to computing. So such as this is a simple function can be approximate f within the error of epsilon for given distance you choose. Okay, the norm you choose. Okay, this f is Rd to R, G can be Rn to R. It's if it, you may think it does not make sense. Even for D equal to N equal to 1, you are basically saying if your G can be chosen very simple, like a line, like a linear function, then you are basically saying you want to use a line to approximate a curve. It's most time it does not work or does not get a good approximation. So what do? You essentially to this make sense, you need to find a map. The map is from Rd to Rn, such that your G composed with T. Then you can have this makes sense. Okay, so all the approximation is you find the G can be, the G has a parameter. You say if G choose linear, you have a parameter A. Then you want to find T. So make it work. Okay. What is the classical approximation doing? Classical approximation essentially T is chosen. It's independent for your F or your data. But it's dependent on the epsilon and N. Okay, you want a small epsilon, you normally have a large N. And the classical learning, I call shallow learning. What's the shallow learning doing? Shallow learning is doing that instead of T is fixed, IT, they also already start to learn T. But you parameter T only have very few parameters for T. So you learn a few parameters. So that's the classical learning. Okay, so shallow learning is doing. Okay, the deep learning, you completely parameterize the T. You make T to decompose to the many simple functions. That each layer you parameterize it. So you have a huge number of parameters to learn. That's the deep learning. Okay, let's look at the typical classical approximation. There's a first example everybody use, is still widely used for linear approximation. Linear approximation is very simple. So given a fixed set of generator, okay, you have a generator, and then you do the kind of projection. That's all. Either linear projection or pseudo projection or interpolation or pseudo interpolation. That's all. So basically, this is what it is doing. Okay. So the classical linear approximation, what's the good? That's good is that, okay, say if you have in the Hilbert space, this you have to do the orthogonal projection. So you to make the good approximation, that means your n go to infinity. You want to this observation far converge to f fast. You need this so-called the inner product of your f with each basis. Base function, the coefficient should decay fast. So you want to see the coefficient decay. That means you need it to be smooth. Okay, that's why in the classical approximation, you talk about the approximation order, you talk about the smoothness. You have to talk about the smoothness. Okay, that's what good. Then another approximation, now also called classical approximation, that's called n-term approximation. So n-term approximation, or it's instead we have a fixed n, you have a bigger dictionary. The bigger dictionary is huge, but you are still in linear, but your non-zero number of non-zero coefficients in your sequence A is fixed, is A. That's called n-term. So that means you have from a dictionary, you pick up n base term out. So this process is nonlinear. First of all, it's nonlinear. So that's why most of the time people call nonlinear approximation in older days. That means it's an n-term approximation. So because you choose for each f, you choose best n term. So this means your decay for the canonical coefficient, decay rate, decay, depending on decay is much less. That means the smoothness condition is weaker than the linear approximation, especially the n-term approximation can go very well for piecewise smooth function. That's why the wavelet approximation is essentially n-term approximation. That's also because of that, this n-term approximation as the wavelets is why waves are good for the imaging. Imaging is piecewise smooth, not only piecewise smooth, it is piecewise constant. So that's why I worked in the last 20 years on the application of the wavelets to the imaging. Why it work? Fundamentally, mathematics behind is this n-term approximation. But both of this classical approximation have a constraint. First of all, you need a certain smoothness, certain kind of smoothness even for n-term approximation. Secondly, it's for lower dimensional case. That D is small. Okay, when in the classical numeric analysis person, people will think D is 4, 5, 7 is already high. But for the now, like for the deep learning, you deal with the D is 1,000 and 1,000. Okay, so for those 1,000 dimension space, so the method does not work. Okay, no matter what you do. Okay. So now, what's the deep learning in terms of deep neural network in terms of mathematics? The mathematics, the deep neural network is very simple. A deep neural network, as I say, this deep neural network, you are basically parameter important. This is a parameter space. Your phi compose that can be decomposed to the air layer. This G is what is G. Then your T can be decomposed to the air layer. Okay. So each Ti is the composition of the two functions. First is alpha map. This alpha map, W is the matrix and B is the vector. All those are parameterized. These are all parameters up to learn. Okay, this is alpha map. Then the alpha map followed by an activating function. So activating function is very, very important. This is a nonlinear activating function. So so each TGA essentially is already the composition of the two functions. Okay, your parameter is W and B. So you put all the parameters together, yeah, you have a huge number of parameters. So deep learning, in some sense, this is the neural network. Okay, you can see many times. This is basically the neural. You can look like that. So what we are doing about the approximation of a deep neural. Okay, so this is phi xa. As I said, this is your phi xa. You have many layers. You want to approximate f, so you have to have a distance. You decide this L is the distance, the distance between phi x and fx, and then you have of course you have a distribution, and then you have to take the average. That's all. So if your distribution, if you take this simple distance and your distribution, uniform distribution, this become your omega is just the cube. Then it's basically L2 norm. Okay. Then the deep learning is theoretically you want to have this one. You want to find the parameter theta d. So this is a parameter to learn. You want to find the parameter to so that this RD theta get a minimum, minimize this RD theta. That's what the deep learning want to do. However, this is suppose you have a function. Okay, you can do even how to do that. That's the model is well defined, but practically you don't have a function. Okay, you don't have a function in your hand. You only have a data in your hand. Okay, so sometimes you even don't have a distribution of the data. So instead of using that model, you use an empirical model. Empirical risk is RS. That's really they're using the data. You use the XI, that's the data you given. Suppose you have given the data, you use this. Okay, this is your empirical model. So your empirical model, your deep learning is that optimize that. you want to the system you can compute. Okay, you can develop the optimization algorithm to do that. So ideally, if you get a model solution that is theta S, you get a minimizer of this cost function RS. Practically, of course, you never get RS. Okay, RS because it's a highly non-convex problem. So you can get RS, you get Rn. You can theta N. Theta N is your numerical solution for 1.1. Okay, that's you get theta N, you get a phi x theta. So practically, we talk about deep learning neural approximation of a deep learning neural network. Essentially you want to find the error that RD at the theta N. That's what you want to. That's what you want to. So if you have a uniform kind of distribution, this is what you exactly want to find. Okay, that's the error you want to estimate. Okay, this error you can divide into 3 cases. This RDS can be, you can manipulate, it becomes 3 terms. Okay, the first term, this approximation error. Okay, this is approximation, that means exactly the function model. The second term, this one is optimization error. And the third one is a generalization error. Okay, so when people talk about this error for deep learning, especially for supervised learning, people talk about the approximation error. I think many of people, they mix it with these 3. Okay, see the mix with it, so it's sometimes very confusing. You don't know which one to talk. Now I want to separate these 3. Okay, so basically, given a neural network, given a width and a depth, then you generate the parameterized space, we call hypothesis space. This is hypothesis space. This is your target function F. Okay, target function is, when I talk about approximation error, is this target function F, and with the distance between target function and the hypothesis space. Okay, then this is basically your base model. That's the RD zeta. Okay, then this is all about optimization. So you have optimization, you get the theta is theta N, I call. This is theta N you have. Then you see this theta N is not a minimizer of your empirical risk. You have an optimization error. And this is an empirical model, and with the best model, you have a generalization error. So in some sense, all your error have a 3 components. You have an approximation error, you have a generalization error, and you have an optimization error. Okay, today I'm only focus on the approximation error. So approximation error depends on your function, your property of a function, depends on your neural network size, but it does not depend on your algorithm, does not depend on your data. Okay, now generalization error is essentially the difference between empirical model and your best model, the function model, your data model or your function model. This part, in fact, is what is statistical learning. All the statistical learning, all the estimate, they are essentially estimate this error. Okay, now from this numerical solution for your empirical risk minimizer to the real minimizer, that's an optimization error. This is the Derfong's search error. Okay, so what's the difficulty for that? What's the difficulty for approximation error? That, as I said, difficult or the theory we needed to build is to build the approximation by compositions of the function. That is not available in the literature. We need to build this. What's the problem for these generalization errors? Okay, you look at if you look at the statistical literature, the generalization error, any kind of analysis, maybe technically different and whatever, all the statistical analysis, basically the rate of the error is something like that. In the denominator is more or less some number. The number related almost up to a constant. Constant is the dimension of the parameter. Okay, this is the numerator. The denominator is what? Is the number of data. Okay, the rate is like that. All you look at all kind of analysis. General results is that sometimes they put the numerator as an entropy or some other covering number, but essentially is related to the dimension of the parameter. Now, for classical learning, it's okay because I said there are only very few parameters. So dimension for parameter is very low. As your data size is big enough, you're okay. For deep learning, there is a problem because your parameter is huge. Number of dimension of the parameter is huge. Most of the time, it's bigger than that number of data. So here you have a problem. Okay, you need to have something different to do. With the traditional method, there are many papers, but I don't think they solve the problem. Now, for optimization error, okay, the key difficult, okay, optimization is developed so long and fairly mature, but most of analysis for complex problem. But this problem is, first of all, is non-convex. Secondly, is a huge dimension. Okay, so this also many things to do. So all these three error analysis, we need to develop new mathematics. Okay, to me, I think the approximation error is relatively simple because it's independent of data, independent of algorithm. And I think for this, both people now try to separate from analysis and algorithm. It's hard. For this one, I can. So I choose the simplest one to do. So for last 3 or 4 years, I focus on that. That's today, I'm going to tell you what my understanding for this approximation error. Okay. Without the approximation error, what do you get? Without approximation error, your problem is that even you have a very good optimization error, you have a very good generalization error. If without this error, you only tell you if your function is in your hypothesis space, you are doing well. Okay, if function is not in hypothesis space, you don't know because this one control your distance from your function to the hypothesis space. All these are within the hypothesis space. Okay, so approximation error is important. So the approximation error I talk about is this part. Okay, is this part. Okay. Okay. So now before I start to talk about, I talk a little bit about the idea. Okay, the key difference between here what I'm talking about here and what the classical approximation has done. Okay, the key idea, okay, key component of the classical approximation theory is very simple. In fact, technical wise, each system is very technical, but idea is very simple. The idea is depend on two ideas. First of all, your system must locally reproduce polynomial. Okay, you look at the spline or this finite elements, all kind of approach. They must have a locally reproduced polynomial. So once you have a locally reproduced polynomial, then you use Taylor expansion. Your Taylor expansion, the first is a polynomial term, you'll be incurred, then you have a remainder term. Remainder term give you approximation order. So therefore, you want to have a higher order, you need to either have a high smoothness. Okay, you need to reproduce a higher order polynomial and higher order smoothness, you get a higher order approximation. That's a classical approximation. Okay, idea is that. Okay, nothing more, nothing less. But what we are doing here, we are doing different. You say what? If you talk about approximation, instead of your, okay, so classical approximation, you normally cut the subdivided domain, make the domain small, so then your step size small, your approximation order is there. But instead of cut the domain, you cut the range. You cut the range, you think about if you have a range, then all the approximation is automatically given to you because You think about your range, at any point map to the range, your range, you cut the small, it's epsilon or epsilon neighborhood, you are done observation. Observation is trivial, but what's difficult? Difficult is you have to know the inverse of the small ball in the range. Okay, in some sense, this is hard. Okay, this is hard to understand. When if a function is regular, it's okay. Function is not regular, it's hard. So in fact, this approach, you need to know the level set of the function. So traditionally, we talk about the approximation. We talk about a good function. More normally talk about a smooth function. But I think for now, for the deep neural network, what is a good function and easy to observe? You have a simple level set. Okay, I think level set, you see about level set, you back that in the high dimension space, the geometry, the location, and the volume, everything plays a role. But if you have a simple, says if it's linear, this is very simple. Okay, okay. You see what this idea is not the first time I use it. Okay, you think about it. You think about it, if it's a Riemann integration is a classical one, is a divide subdivision in the domain. But as the Lebesgue integration, you think about it, it's subdivision in the range. Okay, so probability is related to the second approach. They think about it, but they only need to know the inverse, they only do the volume. They don't care geometry so much. Okay. Okay, if you do the image, the wavelet method and the TV method is a local approach. Okay, and the non-local TV, you look at it, it's essentially this approach. Okay, so that's next. Let's talk about the mathematics. Now we can see it's really about approximation through the composition. Okay, so suppose you have a data. You basically want to find T and G such that T composed with G to have a good approximation. So forget about the neural network. First we think about what the mathematics question we can ask. Okay, first question we can ask is, suppose I have a F and G. Okay, is there a measurable function T such that make F equal to G composed with T? Okay, I give you F and G. Do they have that? The answer, mathematically, we can do it. Okay, the condition is very weak. You just need an image of G, the range of G, as a superset of range F. And in fact, I can weak the condition if G is continuous, but continuous is good enough. Okay, okay. See other G condition, I can do that. Okay, I can always have that. Okay, this condition of this image of G contain image F is clearly you need. If you have F image of F outer image of G, this portion you have no way to approximate. Okay, this clearly necessary condition. What the problem for this theorem is great in the mathematically, but the problem is that my proof for this theorem, the T is existence proof. I don't have a constructive way. Even you give me F, I don't know how to construct the T. I know there exists such T. Okay. So the next step is that, okay, I ask a question. If I given an epsilon, can I do that so that I can theoretically, at least theoretically, I can construct T such that you can do. That you even don't need you just need this image of G is superset of image of F. You just need that. Okay, you don't need anything else. You can do that. Furthermore, if you give me F and G, I can write out of T. Okay, for given epsilon, I can write out of T. Okay, that's no problem. Okay, this in theoretically it's constructed. Okay, but whether this constructive can be computable. This in fact this function is very complex. It's unlikely it is constructible. Okay, so because of that, we will ask the next question is that whether can you decompose T to a few layers? Okay, composition of the T1 up to TL. That each TI is simple. What do I mean simple? like something almost close to identity, perturbation of the identity. Like a projection, I also consider the perturbation of the identity, such that we can learn each TI to do that. Okay, so this one we can do, or not only we can do, we also have an algorithm to do it. Okay, our algorithm is very simple. I don't want to bother you too much about this algorithm. The idea is that each time I have a small net to identify those places for the given data where is not good, not approximate, not where do not have a good approximation. So we identify that using a very small net. Then we improve in the next level so that we using those, we learn further to improve that part of data which don't have a good approximation. Then we combine these two, we get a next iteration. So we go on. Okay, so we can go forever. So the key idea is when do you stop? Okay, very simple. This d epsilon is G is a J's level kind of approximation or error. This is a J plus 1 level approximation error. What can I get is this identity. So this identity key is also R, A, and P. Okay, I have all the exact definition for R, A, and P. But this RAP can not only you have a definition, you also can estimate at each iteration. So if you have estimate that if this number is smaller than 1, you will reduce the error. You will continue. If this number is bigger or equal to 1, you stop. You don't need to go further. Okay, that's what is the idea. So we in fact we try to implement this idea and to do the like a MNIST or fashion MNIST and for the data fitting. And of course, this MNIST and fashion MNIST for the state of arts classification. This is a classification problem. They already done very better, are very excellent. Okay, no one can beat them for much more. I'm not declared that I'm beat their result. We are doing the same result, but with a much smaller network. Okay, that's just the test of the concept. So, okay, that's the mathematical theory. Okay, mathematics, you do have a composition of the you try to go to the composition of the function to approximate the function. You do have a mathematical theory. You do have an algorithm to match with that. Then people will ask, say, okay, you do whatever you do, what with the really neural network that doing the similar things or what you say here. So I worked hard. We found a great example. This regional net. Regional network is one of the most popular network. This especially fully connected regional nets. Okay, fully connected regional nets is basically your iterate. Okay, xk plus 1 equals 1. Your h is your activating function. Okay, for example, using ReLU. Okay, I'm going to show you what's the ReLU, what are other choice of activating function. So your each neural network, what we wrote before, you use go down to the regional nets. That's what it is. So this is the discrete. You can continuous time idealization for that. So it become a ODE dynamic system. Okay, this becomes this one, and connected from the regional nets to this ODE dynamic system is not my innovation, not our innovation. The this I think many people have done that. For example, Weinan and his student Chen Xiao, who is my collaborator, they did it. Maybe they're one of the first group of people did it. Okay, but what they did is different. They did it using that to study the SDE. Okay, the stochastic gradient descent (STD). Okay, method. Okay, that's what they started this one. But we are the first one using this to study approximation of the regional net. Okay, so now we have a control family. Okay, this is the F is the control family. Your theta is the parameter. Your H is your activating function. So you have a huge control family. So where the approximation theory kind of get built in. You have this dynamic system. You have a flow map. You have flow map. Flow map basically map from Tx. When x0 equal x, your starting point, to the end point. That's the map. This is your flow map. Okay, so for flow map is your Tx. You define Tx. This Tx is exactly what we use. It's same as the Tx we did before. So your Tx, even so, your T can become a composition for many layers. Very simple, because your zero, your starting point is 0, end point is tau. You can participate the time domain. You can make the each Tj equal to Tj equal that. Then your T is exactly the composition for that. Okay, that's exactly that. So rest is that this is connected with our previous series very well. The next question is, what kind of condition you want to put on the edge so that G composed with T can have a generate density of your certain function space, the continuous function, continuous space or LP space. Okay, that's what we answer our question. So we have a greater theorem. The theorem says, as long as you are still same thing, you need to range for G cover range for F. You still do that. Then your activating function have to satisfy some mild condition. I will tell you why. I'm not going to tell you what's the condition, but I will tell you why I say it's mild conditions. Then you will have that. Okay. And then you go back to this is the ODE, go back to discretizing, Euler discretization, you will go back to the universal approximation property for residualness. Okay. This paper, if you read this paper is really like a pure maths paper. That's why it's published in the Journal of European Mathematical Society. Okay, it's really like a pure maths paper, but it's really gave us a deeper understanding for the residualness. Okay, now why I say this our condition on this activating function is weak. Okay, commonly we have 3 common activating functions people use. One is ReLU. This ReLU is very simple. ReLU is a piecewise linear spline. Okay, before the 0, your OR 0 from 0 onwards is equal to x. Okay, another is a sigma. Okay, sigma. Another is a tau. Okay, so this okay. There are all other kind, but this is 3 commonly used. But most people have always say we like the activating function like that. You have a very calm here, then they jump up, then stay calm. Okay, so okay, it was the form. This is not. This is one very calm. It's 0. They jump up forever. But if you have two such function combination, you still have they have a 0. They jump up, then they kind of keep it constant. That's so this is the ideal kind of activating function. Always like that. Okay, staying calm, then jump, switch on, then stay, or something like that. Okay, for these 3 activating function, first of all, for this 3 function satisfies our condition. Okay, ReLU, yes, and other like sigma and tau also satisfies our condition. And furthermore, for the real, if you work with this residualness, you know that people don't upgrade each time. They have a block. They have a block and upgrade. So the block structure also satisfies our condition. So all those residualness will have a universal approximation property. Okay, now I move on next. I will do the approximation rate in terms of width and depth. Okay, for given the width and the depth. Okay, given the linear network, the 2 parameters is important. One is the width, another is depth. Okay, given the width parameter is n and the depth parameter is L. What are the okay? Now the activating function is the ReLU. Okay, approximation rate for the in terms of n and L. So we have this result. So if f is Lipschitz with a constant lambda, then you have this. This is basically you have n and L, and this is in terms of n and L. Okay. Okay. This you have we have exactly estimated the the network size and the approximation rate. Okay. And furthermore, this is optimal in the sense lower bound is the same. So its upper bound is also lower bound. So you have no way to improve. Okay, but you can generalize this to the instead of Lipschitz, you can say it's for continuous function. Continuous function, you have to introduce the concept, the module of continuity, but I don't want to bother too much, but you have a similar results. Okay. Okay, so what's the literature? The literature so far, okay, for L equal to 1, that means you are just one layer, hidden layer. L equal to 1, it's a well known. People always believe rate is n1 over d. Okay, and in fact, this d equal to 1 I know it when I was a student, but for d bigger than 1, everybody says it's true, but no proof. Okay, you can prove it, you cannot exceed that, but nobody has a complete proof for that n bigger than 1. That's exactly this one. Okay, even for ReLU. Okay, no proof. Okay, this is our paper is in the later 2018 and early 2019, and but Yarlowski, he had a paper in the 2018. What he did, he said, okay, I pick a special n equal to 2d plus 10. That's a magic number. Okay, d is the function domain dimension. Okay, then he's one is asymptotic time analysis. He said then your L is sufficiently large, as long as you have a season rate. Okay. But when we did it's also 2018, we have a n equal to L equal to 2 or 3. We have a season result first. Okay, this paper, we have a first that was excited because but we know that L equal to 1 doesn't work. L equal to 1 at most 1. Here we have 2. But finally we get for arbitrary n, arbitrary L. We calculate the size and rate exactly in terms of n and L. It's not asymptotic. Not to say you have a sufficient large n and sufficient large L. So that's a big difference. All the technical is go down to you want to have an exact estimate of the rate, not asymptotic analysis. So that's the hard part of our analysis. In fact we have a 3 paper on this topic. Okay, we wrote 3 paper on the ReLU optimization for approximation for the continuous function. Okay, as I said, this is the best you can have. You cannot improve further. Okay, this people are not happy because you still have a 1 over d. Okay, when d is huge, they're still not happy because this means curse for dimensionality. Okay, many people are not happy, but this you cannot. If you want to reason ReLU, you cannot do further. So what are we gonna do? You have you can do the first 2 things. Either you reduce, make instead of a continuous space or Lipschitz space, you make a smaller space, function space. Okay, so I can go to small, I can go to extreme, as small as a polynomial space. If I have a polynomial space, I have a very good approximation rate. So approximation is that if you degree the k, your neural net size is width is about that related to k. Your depth is that, but your approximation is much better. It's exponential, no curse for dimensionality. You have n is width basically, and your power is k times L. Okay, but it's a polynomial space. You have good observation. So as I said, you get a hint from a classical approximation. Classical approximation want to reproduce polynomial. Neural network for the ReLU, you cannot. You can only reproduce polynomial with degree 1. So, but they can approximate high degree polynomial as close as you want to with exponentially fast. So with this one, you can see I kind of have a better rate for smooth space. Okay, for the smooth space, you can see you can have this kind of rate. Okay, smooth space, you have N. If your smoothness is S, you have a component of S. Of course, people say, okay, your S is big enough, bigger than D. You're kind of overcome a little bit of cursive dimensionality. Okay, so your space must be smooth, but your smoothness is high. Your neural network size also bigger. Okay, but it's still manageable. Okay, deficit is all this because the constant is related to D and S. Okay. So another way is, of course, you do what? You do change the activating function. So instead of using one activating function, I'm using two activating functions. Say floor plus ReLU. I have a choice, free to choose two. Floor function, okay. Floor function is very simple. Okay, it's piecewise constant. ReLU is piecewise linear. So I use this function that basically the neural network is the same. Basically each time I can have a free to use this one of them, ReLU or floor. For given that, what the result? The result is surprising good. Okay, forget about this is a continuous case. Let's look at the whole continuous. Say when the Lipschitz is alpha is 1. So this is what you have this doesn't matter. This you already get rid of what cursive dimensionality because this D doesn't matter. Here you have a N is the width essentially, and here you have a power is the square root of L. L is the depth. Okay, it's not as good as the polynomial space, but it's very good. It's almost like exponential. Okay. So in fact, you can even do better if you use 3. Okay, this is the 2 papers we had in this direction. Okay, now the most recent result, I'm going to talk about universal approximation property. Okay, I have a simple, this is the very computable kind of activating function. This is activating. So from the minus infinity to 0, it's like this function. This is called soft sine function. From 0 to positive infinity, this is a piecewise linear, this is a triangle wave function, and with period 2. This is a simple function. Okay, in terms of computation for this function, is almost the same as the ReLU. Okay, this is a function. What is this function? What is this magic function? If I develop a neural network, the same as a ReLU network, just replace ReLU by this activating function. Okay, this is the same neural network. Only my sigma is the function I have before. Okay, here I introduce a hypothesis space. I talk about a hypothesis space. Here I introduce a hypothesis space. The hypothesis space is this one. The hypothesis. The hypothesis space H is that, okay, given N and L, basically you are with the depth and width, you have you generate the parameter space. This is my hypothesis space of neural network with N width and L depth. So magical theorem says for this hypothesis with fixed N and L, as long as your L bigger than 11, your N basically at the order of D squared, you have this hypothesis dense space is dense. So that means you have a finite number of neuron which can dance in the whole continuous function space. Okay, this is a magic because why? This theorem indicates that that's what if you still you have a universal approximation property with a fixed number of N and L, as long as your N and L bigger than the 2 magical number. And in terms of if people still talk about an approximation rate, that means your rate is because for actual epsilon, you always kind of have an F in that, so that's smaller epsilon. That means in terms of rate, it's like infinity. Okay, so this result, I'm really happy about that result. This is our new result. I'm very surprised. Okay, so as I told you, people normally don't like this this kind of activating function here. You have this triangle wave. People want to have a signal type of function. So something like this function. You have almost like a from a minus infinity to almost like a close to -1. Then you switch off. Then you close to stay on 1. So we can have a this function. This is sigma tilde. Sigma tilde is basically as simple as that. You can these functions still can have a good approximation. So this hypothesis space will dance in that your L instead of 11 it becomes 66. Your N becomes that. In fact, we have a bigger class of function have all these kind of good approximation. Okay. So this function not you can write that out. Okay. Another thing. Okay. One with for supervised learning, I think one with the biggest success is the classification. So for classification, it's very simple. In fact, for example, you want to approximate a function is very simple. You have a two domain, omega 0 and omega 0 of the binary classification. We have omega 0 and omega 1. You have to want omega 0 equals 0, omega 1. You want to approximate this function. Because look at the function, very simple. That's exactly the point. The point is what? Because this X is a very high dimension, because each image, you have the black and white image. That's the 256 by 256 dimension space. Each point, each image is 1 point. So this level set is very complex, but the function is simple. Level set is extremely complex. So the classification is what? Okay. We can show that your F, this kind of F is in your hypothesis space. Not to say approximate, can be approximate. It's exactly in that. As long as your omega 1 and omega 2, omega 0 and omega 1 has an empty intersection, the closure of that. Of course, if they don't have this property, you cannot separate. Doesn't matter what it is. Okay. So this theorem can be, of course, generalized to any number of the classification instead of the binary classification, you can M class classification. This is over there. So this is very important, because this means that's also indicate why this deep learning is very good for the classification. Essentially, you don't have approximation error. Only error you have is generalization error and optimization error. Okay, this is our new paper. I think I just finished last month. And okay, to summarize, okay, what I'm talking about here is approximation error. Okay, so approximation error, we gave the exact estimate, and also in some cases we can say this approximation error can be as small as you wish if you use this nice activating function. Okay, so but this does not mean we solved everything about this deep supervised learning error. Supervised learning error, you have two more. You have optimization error, you have a generalization error. You know, okay, some people complain why we should go through this path. Can we have a direct algorithm go to your approximator? Approximator is maybe directly. So that's open, but you need to have some computational way or algorithm or model to do that. Okay. Okay, I think I finished here. Thank you.